Hello YouTube. Today we continue our discussion of simple electricity, and I would like to remind you that in our last discussion session we introduced electrical resistance, and we can represent electrical resistance in electrical circuits with a resistor. So this is a sign for resistor with electrical resistance R. So now we would like to consider what happens when we connect several resistors. We will consider two resistors in series and parallel. So let's see how we can calculate its equivalent electrical resistance, and also how we can show it, demonstrate it experimentally. So let us start with series connection of two resistors. So let us extend this electric circuit. So it will be resistor R1, here will be resistor R2, and let us connect these two resistors, which are connected in series, to some power supply, DC power supply, which creates some potential difference at its terminals, delta V. So obviously from this electric circuit we see that there will be some electric current flowing through this circuit. So let's denote it as I, capital I. So now the question will be how we can replace these two resistors with some equivalent resistor, which will in this being connected to the same power supply with potential difference between terminals delta V, will result in the same current, capital I. So here we can show another equivalent circuit, which will be R equivalent connected to the same power supply minus delta V, and that will result in the same current I. So we want to figure out what will be this R equivalent. So what we can write here from the continuity of electric charge distribution in the electric circuit, current through resistor 1 and current through resistor 2, I2, they will be equal, and they will be equal to this capital I. So we can write that capital I is equal to I1, and this is equal to I2. So we don't have any deviations, any branches of electric circuit, so this is only one loop. Current will be the same in every point of this electric circuit, means current I, capital I, will flow through resistor R1 and resistor R2. However, we need to mention here about voltage drop over each resistor. So here will be delta V1 and here will be delta V2. So we have some voltage drop over these resistors, and in this case, when we have connection of resistors in series, we can write that total voltage applied to the circuit, which is delta V, potential difference at the terminals of the power supply will be equal to the sum of delta V1 plus delta V2. So now, if we consider the integral form of Ohm's law, we can write that in general that delta V should be equal to current times resistance. And in this case, we can put here equivalent resistance. So we will write it based on this equivalent electric circuit. So now for delta, instead of delta V, we can substitute I times R equivalent. That will be equal to I times R1 plus I times R2. So we can write also, express this delta V1 with product of electric current and magnitude of resistor R1, and the same we can do for delta V2. So now we can cancel out this current, and we see that R equivalent is equal to R1 plus R2. So that is expression for equivalent resistor, which can substitute these two resistors R1 and R2 when they are connected in series. So we just have shown here that if we have series connection of resistance, the total, like equivalent resistance, will be equal to sum of all these resistors. So let us demonstrate that in practice. So for that purpose, I have some set of resistors which we can use for our demonstration. Let us pick up some with more or less round number, like for magnitude. And here we have, probably you see this, 1 kilo ohm resistors, like plus minus 5% accuracy. 1/4 of watt power which can be dissipated on these resistors. So you might have the same magnitude of electrical resistance, but resistors might be much larger. In that case, possible dissipating current, possible dissipating power will be higher for this resistor, so they can be different in form factor. So let us get two resistors. They're supposed to be 1 kilo ohm each. So we have two resistors which have the same magnitude of electrical resistance. So let us use multimeter to measure actual resistance of these resistors. So resistor 1, you see it is almost 1 kilo ohm, 998 ohm. And resistor 2, again 988 ohm. So the units here are kilo ohms. That's why we see it as 0.999. So that means we have 999 or 98 ohm. So very close to kilo ohm. So now what we will do, we will connect these two resistors in series. Let's just mechanically connect them. So that's not the ideal way to do it, but good enough for this demonstration. So now we have literally connect two resistors in series. So now let us try to measure resistance of this battery of resistors. And let's see what it will show us. So we have 1 kilo ohm, 989 ohm. Well, it's almost 2 kilo ohm, which is the sum of electrical resistance of each of these resistors. So we have it twice larger because we connect in series two equal resistors. So it's just to demonstrate with real life experiment that the derivation of this conclusion about magnitude of equivalent resistor when we connect resistors in series was correct. So we will use these two resistors for another demonstration, so we still keep them somewhere around. Let's put it here. And now we will switch to parallel connection of two resistors. So let us clean this space, and we will now consider two resistors connected in parallel. So we have resistor 1, R1, then we have second resistor, R2, and they are connected in parallel to each other, and both of them are connected to power supply, DC power supply, with some voltage, like potential difference between the terminals of the power supply, delta V. So what happens now? We will have some potential drop over resistor R1, R2. Let us denote it as delta V1 and delta V2. And also here will be some current I. There will be some current through resistor R1. It will be I1, and current through resistor R2, I2. So here we have some junction, and this current I will split in two components, I1 and I2. And from conservation of electric charge, we can write that current I is equal to I1 plus I2. So another important point here is that potential drop over resistor R1 and R2, delta V1 and delta V2, they are equal, and they are equal to the total potential difference between the terminals of the power supply, because all these terminals of resistors connected to the same terminals of the power supply, since we have parallel connection, and with parallel connection of resistors we can write that delta V is equal to delta V1 and is equal to delta V2. So now we want to find equivalent resistor of this resistors R1 and R2 connected in parallel, and this will be R equivalent, again connected to power supply, delta V plus minus, and in this case there will be some current I, the same as here, flowing through this electric circuit. So we want to know how we determine this equivalent electric resistance. For this purpose, we should express the this current I from Ohm's law in terms of potential difference delta V and equivalent resistance. So instead of I, we can write delta V divided by R equivalent, and that will be equal to delta V1 divided by R1 plus, instead of I2, we put delta V2 over R2. Considering that delta V1 and delta V2, they are equal to delta V, we can cancel out these potential differences in numerators, and we end up with such expression. 1 over R equivalent is equal to 1 over R1 plus 1 over R2. Or we can express from here the final equation, how we determine equivalent resistance. That will be R1 times R2 divided by R1 plus R2. So following our previous example, when we had two resistors equal to each other, so we can assume that R1 is equal to R2, and for this case R equivalent will be equal to R squared divided by 2R. So we can cancel these guys, and that will be R divided by 2. So what it tells us, if we connect two resistors with the same magnitude, equivalent resistor, connect them in parallel, of course, equivalent resistor will be twice smaller than individual resistor which we use in this parallel connection. So let us demonstrate this with repeating our previous experiment, but in this case we use the same two resistors. We know that they are each resistor is 1 kilo ohm resistors, and now instead of connecting them in series, we can connect them in parallel. So we connect both terminals from both sides. So this is one connection here, and here is another connection. Okay, so we have this kind of structure. Now, two resistors connected in parallel. So let us measure resistance of these two resistors connected, identical resistors connected in parallel. So now we place terminals of the electrodes of this multimeter, and what do we see? We see 500 ohms. Now units are ohms, so we have 499.4. You remember they were not exactly 1 kilo ohm, they were a little bit less. That's why we have 499.4 ohm, which is twice smaller than resistance of each of this resistor. With this, I would like to finish our discussion today, and we went through, like summarizing, we went through the connection of two resistors in series. We figure out that equivalent resistance is equal to sum of resistance of each resistor connected in series. Also, we considered in details connection of two resistors in parallel. In that case, we have equivalent resistance, which is smaller. It will be always smaller than the smallest resistor, which is connected in parallel. If we connect two resistors which are equal to each other in magnitude, then the equivalent resistance will be twice smaller than individual resistance. So thank you very much for attention, and see you next time. Bye.